Good evening and welcome, everybody. This is Obi-Wan Pez for N Simplex Pachinko. Good evening and welcome. So, Mega Monkeys. Excuse me. Welcome on in. Penn Center, welcome on in. Good to see you all again. Or for the first time, or wherever we're at. It's just great. Alright, so... got the calculator, got the monitor. Got the introduction of tensor calculus, just in case. Hello! So, tonight I wanted to talk a little bit about, yes, so, tensor calculus is a branch of, calculus, but, like, it's kind of a combination of linear algebra calculus that allows you to expand a lot further and to start doing... Oh, no. See, I said just in case. Whew. Those are words. So anyway, I do want to talk a little bit about some stuff I was talking about with my students on rational equations, rational functions, but that can wait until whatever other conversations are done. So, does anyone have anything that they want to talk about tonight? Any cool stuff they've learned? I got you. Hey, Super Brain. Been a while. Good to see you. Glad you can make it. Let's see if... yeah, okay, it is here. Oh, got my YouTube handle notifications coming in. Cool. Okay. I did not have any particular questions that came in. Hey. Alright, so, if anybody has any particular questions, let me know. And apart from that, I will just be dancing around with some other stuff over here. Alright, so, my students and I were talking today about rational functions, which are going to be those that they're real-valued functions. You know, we're only talking about real-valued functions, so we're just throwing that out there. End up being, let's see, P and Q are polynomials. Shifted on me. And Q of x can't be 0. So as we define this, we said, okay, simplest one that you can come up with, and they were like x. And I was like, all right, well, okay, fair enough. Simplest one that we haven't talked about. So first parent function that we talked about here in terms of rational functions that are not also polynomials, like plain polynomials. So if q is a constant, then, right, it's just going to end up being a polynomial. And we just finished that section, so, like, let's move on. So we get f of x is equal to 1 over x, also known as y equals 1 over x. And I said, you know, the thing I like about this is that it can be expressed also as the product of x and y is a constant. And this allowed me to... There we go. This allowed me to, you know, show them that it actually becomes fairly easy to figure out what your problems are with this particular function. So in this case, we have our domain of f is going to be all real numbers with the exception of 0. So x can't be 0, and that's going to be pretty obvious in this particular case. Oh. It's a bit loud. See, I didn't think it was loud on your end. I thought it was just my end, but touche. Boop. All right. Now that also may have knocked it out of your hearing range, but all right. This will be quiet for about 40 more seconds, maybe. We'll see how it goes. I think that'll do it. Okay. Yeah, I was never intending on competing with the music, but still have it available for background ambiance, if you will. Okay. So the domain of our particular function f is going to be that x is going to be all real numbers with the exception of 0, and I said you could do that, or you can go the other way. Negative infinity to 0, union 0 to infinity. Of course. And then when it was originally just in this format, I said, okay, so what can y be? And they were like, well, all real numbers, because it's this other thing. And then somebody said, well, y can't be 0, and I said, why not? And so like, I don't know, it's just cuz. And okay, some of them have prior knowledge about what's going to happen with asymptotes and things like that. And I said, you know, in this particular case, if you're just looking at the function itself, y equals 1 over x, it might be a little bit difficult to, like, guess what y values are going to cause problems. And again, you can kind of think about it in terms of what numbers don't have reciprocals, because these are just reciprocals of each other. Right. But if we knock this over here instead, this becomes way easier to figure out, because here, this just says that, well, x and y can be any particular number we want as long as the product of x times y is not 0 itself. Or, I guess, individually, it ends up being that the product can't be 0. It could be literally any other value. Okay. I mean, their product can't be any other number other than 1, but nonetheless, you could say here, right, that if x equals 0 or y equals 0, then the product of x and y is going to be equal to 0. We know this from the zero product property that we did, you know, in polynomials and all that. Which part's that, Superbrain? Oh, multiplication is commutative. Tom Lehrer. Where's that one? Is it a particular lecture series? Right, so then here we say that, well, if either x or y is 0, then we end up having that x times y can't be 1. Yep. So, if we go with this, we say, okay, we can't have, yeah, if we let x equal 0 or y equals 0, then we end up with this thing. So we say, okay, x can't be 0 here, y can't be 0 here. So, exact same reasoning that all of this works. Naturally, I was a little more articulate with them because, you know, it's my class. All right. So one of the other things that I am prone to do, Mega Monkeys, if I don't remember, well, I wouldn't know, I guess, your viewing history, so I don't know that you've seen a bunch of my, like, transformation videos. So yep, we ended up talking about how this relates the multiplicative inverse of everything, because here again, x times y is going to get us 1, so that's going to give us the multiplicative inverse properties. And I also had them looking at there was another reason. Yep. Oh well. This was like right at the end of class, so there's a bunch of stuff that I'm like, oh, whatever, we'll just kind of throw stuff at the wall and see what sticks. So anyway, one of the things that I'm prone to do is talk about function transformation. So in the case of y equals 1 over x plus 2, we could say, based on what we had mentioned before, okay, this is all function transformations are going to be of the form y equals a times f of b times the quantity x minus c plus d. Yeah. It's generally why I try to keep it in highlights, so there's always like a backlog that you're able to play. I am occasionally moving stuff over to YouTube as well, but like, I don't know. And with more people going over there now because Twitch is changing its rules, it's like, might get more of an audience over there, I don't know. But then there's so much overlap from 1 week to, you know, 2 months after that or whatever. Whenever somebody asks. And then I'm gonna really have to be more mindful about like updating the actual descriptions of things, because yeah, it's gonna make it a lot easier to find what you actually need. Anyway, with this stuff, right? We say that our a and our b values are going to be multipliers, and these do a vertical stretch and a horizontal compression. And then our c and d values are shifts. C in the opposite direction that's shown, and D in the same direction that's shown. Inside is all horizontal, outside is all vertical. So when we start looking at that, we say that here this is the same as our original function up here, f of x plus 2. So therefore that's f of x minus negative 2. So it's going to be a shift 2 to the left. That's my left. 2 to the left. I'm usually better because I'm facing my students, so like I know that this is their left automatically. I know this is their right automatically. I don't even need to look anymore. Then I face the board and go left, and I'm like, nah, okay. So we know that this is a shift 2 to the left. So that means that our, forbidden value is now going to be where x plus 2 is equal to 0. Okay, you could do that here. Yes. Actually, I just taught that in calc. Because that's like super impossible to try to do the log in terms of your super impossible to do your derivation of derivatives through the definition of derivative thing. Touche. Forgot your parentheses, sir. All right, so here you can just know from function transformation that this is a shift of 2 to the left. Or you can say the denominator can't be 0. So, x plus 2 can't be 0 here, which means that x can't be negative 2. Or you could say that this is going to be x plus 2 parentheses times y is equal to 1. Man, I don't know I'd be throwing fists this early. And again, from here you say, okay, what numbers can't we have? So again, x plus 2 and y individually can't be 0, so those are going to be our asymptotes. And this works for any function transformation. So if you went with something like y equals 3 divided by 2x plus 1 minus 4, you could look at this and just be like, I don't have to know all of the individual function transformations. It's nice to know, but you don't have to. You could also say that this is going to be a y plus 4 over here, and this x plus 1 can be multiplied over to the other side. And then you're equal to a 3/2. So your a and your b value are now both just on the right-hand side. And then when you look at this, you're saying, okay, well now x plus 1 can't be 0. And y plus 4 can't be 0. Right? This is really what I'm going for, is let's yes, let's help students, but let's also teach each other cool stuff. Yep. And you're using logical conjunctions here. So, the Boolean and is going to help us understand that, okay, these are both going to be asymptotes for this thing. We have to have that x can't be negative 1 and also y can't be negative 4. Yeah, as long as it's function transformation, right? So as long as you have this in this format for either of your parent functions. So, I mean, realistically, this is going to be, y equals constant. So let's just do the same numbers again, but x plus 1 to the n. I don't even care what n is, minus 4. Right? So any particular n value for this is going to get us the same function transformations. It's just going to change the behavior of the individual parent functions. So we still end up with our y plus 4 over here, and then also multiply by x plus 1 to the n, and then we get this equal to 3/2. And again, x plus 1 can't be 0, and y plus 4 can't be 0. I can't do a comma because that means or. I know not strictly, but still. Alright, so no matter which way we go, we end up still with this thing. So as long as it's in transformation form, then that's okay. Where we run into trouble is like when it's not transformation form, and I haven't shown this one to this group of students yet. We've already done it in my combined pre-calc class, which does all of pre-calc in one semester. It's 5 credit hours, so it's already condensed enough. But like y equals 3x squared plus 7x minus 4 divided by 8x cubed plus 7x squared minus 8x minus 4. I'm just messing this all up now. Right, so if we want to graph this equation and try to do all that stuff, Yeah, and like I said, it's a 5 credit class. It should be 6. Um, like everybody keeps trying to take it, and we're just like, you know, I keep asking the advising department, are you like restricting the people who can come in here? Because you should be. And they're like, no. Also coming down the pipe for any particular colleges that are out there is the idea that we might be moving some of our classes, those that are more naturally suited to it, to a 7-week format. And so it would be the uh, double the amount of credit hours over a shorter period, but then it would count same number of total credit hours for its 7-week semester rather than the full 15-week semester. So our dean was like, so start thinking about classes that would be like naturally suited for this, and I just put up my hand, and he's like, yep, okay, gotcha. And I was like, honestly, we can just dissolve my entire class and make it 7 weeks, get credit, and 7 weeks. And he was like, yeah, okay. So, like, basically, I am, I am writing a course review this semester whose, like, justification for existing is going to be this class should not exist, and it's going to be dissolved into 2 7-week classes so that we get a checkpoint in the middle of the semester, middle of the semester, where you can get credit for the first half. So basically, I just need to make my write-up include that. Uh, but a lot of classes a lot of schools are debating moving many of their classes to 7 weeks. And our entire math division's like, okay, so pretty much like everything above calculus is just a no. No. Unless there is like humongous, yeah. So I mean, we have 2 classes. We have 2 separate classes. Plainland, yes. But yes, Mega Monkeys, yep. Implicit differentiation. There are 2 ways to go about this. So one, and this is a formula that I only just learned about this semester, because our OpenStax book uses this, but none of the other classes that I have ever taken or taught have ever used this before. So we know, for example, that f of f inverse of x is equal to x. Fair? I'm not even going to wait for you to reply. So I am then going to take the derivative with respect to x of both sides. This only requires a justification of the chain rule. Yeah, that. So here, we say that we're going to take the derivative of f first. So this is going to be f prime of f inverse of x multiplied by chain rule, the derivative of the inverse function of f of x is going to be equal to derivative with respect to x of x is 1. And then we're trying to solve for this thing in the first place, right? We're trying to solve for that one, which is the derivative of the inverse function. So move this over. So this is going to be that the inverse function derivative is equal to 1 over f prime of f inverse of x. Right, and it does have to be 1-to-1 over some given interval. Otherwise, it doesn't work. But this is the idea. Yeah. It ends up being that you could just say, well, if I have the function f of x is equal to e to the x, then f prime of x is equal to e to the x. F inverse of x is equal to the natural log of x, and then this means that f inverse of x derivative is equal to 1 over f prime is going to be e to the x, but it's e to the f inverse, which is natural log of x. So this is 1 over x. So I plugged that in and I was like, wait. Sheesh. Right? And this also works with literally anything else. So this is the log base 3 of x. Oh, no, sorry, that's not f. F is going to be 3 to the x, so therefore f inverse is going to be the log base 3 of x. And then we go with f prime of x is equal to also 3 to the x, but then times the natural log of 3. So then f inverse of x prime is going to be equal to, and again, let's separate this out here. Haven't forgot you, Blainlin. I'm still prime. It's going to be equal to 1 over 3 raised to the log base 3 of x times the natural log of 3. And so this is going to be equal to 1 over x times the natural log of 3. Yep. So that was my holy shit kind of moment where I went, why did I learn this as an undergrad? This thing right here. And it's super easy to derive as long as you know the chain rule. Okay, so then the other one that I did. Okay, one last one. Yep, one last one before we move to blameless question. Which angular momentum, right? Partial fraction power series. Nice. Yep. So actually, right, any of them. It doesn't even matter. Do any of the inverse trig functions. So we did cotangent inverse right up front because I was like, I bet you don't know this one right offhand. And they're like, yep, nope. So I was like, all right, cool. This is going to be our f inverse of x, which means that f of x is going to be the cotangent of x. They did remember, right, that f prime of x is going to be equal to the negative cosecant squared of x. Said, all right, good job, we got that. So then we said that f inverse of x parentheses prime in this case is going to be 1 over. Here again, we take f prime, which is the negative cosecant squared of f inverse, cotangent inverse of x. And I said, I bet none of you know this, right? And they went, yeah, no. And I went, well, good, because we're not done. So we said, okay, this, if you go back, this is an inverse trig function, so we input a ratio. So x over 1 is going to be the cotangent. What's cotangent of theta? Okay, well that's going to be our horizontal versus vertical. So I said, great, let's draw a triangle. So given that this is our angle in question, again, we can call it theta if we really want to, or y, or whatever else you want to call it, or just inverse cotangent. Right, cotangent inverse of x is going to be the angle here. So then what's the thing we do, right? It's going to be adjacent over opposite, x over 1. And then you go with, what's the hypotenuse? Well, the hypotenuse now is going to be 1 plus x squared. Cool. So now, what's cosecant? Well, cosecant is 1 over the sine function. So what's sine? So that's going to be opposite over adjacent, or opposite over hypotenuse. But now it's in this format, right? We want the cosecant. It's going to be equal to 1 over negative. Cosecant is going to be the hypotenuse, 1 plus x squared, over the opposite. So that. And then this is parentheses around the square root portion, squared, because it was cosecant squared. So now this is going to be equal to 1 over negative, parentheses, 1 plus x squared. And I said, if any of you forget any of your inverse trig stuff, now you don't need to memorize it. All you really need is this thing right here. Right? Know how to find the derivative of an inverse function of any kind. And then, et voila, it works. Yeah, I have a pretty nice stack of exams in front of me, too. I'm not going to hold them up because, you know, FERPA. Alright, so this is the cotangent inverse of x square, prime. Trick. Oh no, that's not the website. Damn. Oh, it's .com. Okay. Damn it. Boop. All right, let's get my moderator out here to erase that message. No? Really? Huh. Interesting. No? Okay, interesting. Yeah, so nixthetricks.com. Table of values. Yes, so basically, a table of values is that you are going to take a function, like this, and say, I want x values compared to y values. So in the case of 0, for example, we're going to get here 0 and 0 minus 4, so that's a negative 4, divided by 0, 0, 0, negative 4. So negative 4 over negative 4 is going to be a 1 for y. If we then want to go on and say, okay, what's 1 and negative 1, we can also do the same there. So plug in the individual values in here, or if you're going to do it really quickly, you can use your calculator. So plug in your calculator, and if you've got a TI, then the way you want to do this is to plug in your particular function into your y equals menu. Squared plus 7x minus 4 divided by parentheses 8x cubed plus 7x squared minus 8x minus 4. Alright, and then hit the they're all treats. And then go to second graph is a table, which if you do table set, generally speaking, it's going to be on independent. There we go. It's going to be on independent, ask, or auto, and I'm going to start with 0 and a change in table of 1. When you do that, you can go to the table then, and then get your individual table of values like this. I don't think we can get this as a... Let's see. I'm going to try to see if I can make this a fraction. Yeah, I can. Nice. So... so here, yeah, we end up finding out the fractional values for all of these as we go down the list. Alright, we can find individual values, which are going to end up being our, like, near where asymptotes are going to be. There's nothing particularly nice at the moment. None of our asymptotes are nice values. At least not for this thing. Hand out pocket calculators. And one for you. Man. I'm not going to his house. Okay. So angular momentum is sort of similar to linear momentum. The problem is that because you are going in a sort of circular path. Oh, by the way, on the bottom left corner of that page for Nix the Tricks, there is the link to download the book. So you can download the book for free. Anybody who does have the means, I would, throw a couple of bucks their way if they have a donation thing somewhere. Oh, at the top left also, download. Big giant link. So this is by Tina Cardone, and she solicited a bunch of ideas from the rest of the mathematics community to go out there and nix the tricks. So try to understand that if you're teaching something that is like, here's how to get the answer, but it doesn't really help you understand it, then we're trying to get rid of that. Yes, we. I have made myself part of that community, even though I have never talked with any one of them. Alright, what did I want to do? I was here. What was I doing? Pre-calculus. Oh, angular momentum. 3 left seconds. How's it going? Okay, so yes, in one sense. So angular momentum is going to be the derivative of the force, which, again, it's sort of the same as what we were talking about before. It's working off the second law of motion. Good luck on the ASVAB tomorrow. I think you'll do great. Alright, so angular momentum is going to be it's usually known as L. Oh, good. Is... Alright, derivations from other quantities. So L is equal to... Right, the moment of inertia times omega, which looks like a vector. Moment of inertia, and I don't know what omega is. Where are we? It's omega. And hey, Bertram, welcome in. Where are we? Moment of inertia. Damn it. Is it torque? Sorry. Come on. I mean, like, it should just be listed right at the top, but it's not. That's a real pain. Oh, angular velocity. There we go. Omega is going to be the angular velocity. Okay, so your moment of inertia is the thing that is going to prevent it from moving in a rotational way. And your angular velocity is just how fast is it going at this particular point with this particular vector. Keeping in mind, vectors are straight. So any object can be looked at with this particular vector space. So let's see, when I was grabbing my steering wheel, the position is given by your pointer, saying we are here. Our angular velocity as a vector is going to be given by the thumb, which is tangent to its current path. So this is the kind of like derivative of the position function. And then your middle finger is going to be the acceleration along that curve. So it's going to accelerate toward the center of the circle as it's pivoting around this thing. And you must live in LA. Ayo. Not really. Anyway. Alright, so if you don't like moment of inertia and angular velocity, that's okay because there are other formulations, including the cross product of the position vector r crossed with momentum vector should probably shorten this thing up so it doesn't look like an X, so you all don't think it's a variable, because it's not actually a variable. This is a cross. Alright, so R cross with position cross with momentum. And if you don't like that, rho is equal to mv in Newtonian mechanics. So R cross parentheses m times velocity vector. Okay, so that's going to be just your mass, which is a scalar, and velocity. as a vector. So one of these formulations should work out for what you want. The angular momentum is going to be like, you know, how much does it kind of want to keep spinning along this particular trajectory? Oh, you're gonna make me open that book, aren't you? Alright, hang on. Where's Krasik? Uh-oh. Oh no! Nope, don't fall over. Saved him. Alright. I have a box, little miniature box here with miniatures in them. And if they fall over, they're gonna get cracked. Alright, here we go. Krasik. Erwin Krasik did a book on advanced engineering mathematics. This is basically multivariate calculus, linear algebra, and differential equations just all rolled into one. So applications is very specifically for applications. So angular momentum. I mean, we got like angular speed. Maybe it's just under momentum. Y'all are explaining it just fine, so you probably don't need me. I've got momentum. Or moment, but not actually momentum. Interesting. Let's see. Moment of inertia, 436. Maybe? That's double integrals. Angular speed, 381. I didn't really notice what the song was, but that's interesting. Yeah. RP is, or R cross P is just being given as the moment vector. So, yeah, now I'm not getting anything particularly more helpful. Velocity of a rotating body. So that might be able to help you decipher what the individual velocities are at a given time, given the angular velocity and the moment of inertia for that particular object. I mean, quantum physics really is where, like, what's his name? Einstein really needed tensor calculus. Well, I guess quantum mechanics more. Come on now, Einstein, relativity. Yes, and quantum mechanics does not work the same way as Outer Wilds wants you to think it does. Something does not enter a quantum state and disappear on you. As much as awesome as that would be. Oh, do I have my... Oh, man. Oh, wait a minute. I have a print version of it here. Anybody who hasn't been here for a super long time, made a dungeon for some of my my friends' characters in Titan's Grave because they were being naughty. I was like, okay, fine. You guys want a FAFO? Let's FAFO. They were like, oh yeah, we can just like defile the gravesite of this like local hero. I'm like, oh. The constable showed up and was like, what in the hell are you doing? So they were about to be chucked into a prison, which looked like this. Likely, it would have been some far branch on this one over here. Some far branch over here, which would drop them into the middle of, you know, further branching and further branching and further branching. And what would happen is that the room, each number would be labeled with a room, very much like Cube, actually. There wouldn't be as many traps as Cube, because that would just be mean. And not one of them was a mathematician, so that can always make it very interesting. Probably one of them had heard of, actually one of them was a mathematician, but probably at least one of the others of them had heard of the Collatz conjecture. And so this is that pick a number, any number, and if it's even, divide by 2. If it's odd, multiply by 3, and then add 1, and continue. So keep repeating the pattern over and over and over again. Eventually, you get back to 1. It's been proven for all numbers up to like several million, but it seems to be, at least at the moment, seems to be unprovable that every single number is represented here. So it's an interesting diversion from reality, and so I started using this, or I was going to use this as a prison for them, because again, they were being naughty and defiling the gravesite of a local hero. So I was like, okay, constable's gonna lock you up. Like I said, throw them down here somewhere, and then they'd have to work their way back, figure out the pattern first, and work their way back. If they ever got onto a branch that was just going to double every time like this, and never have a something that's divisible by 3, because that does happen occasionally. Oh no, if something is divisible by 3, then it'll just keep having a branch which keeps doubling on to infinity, and it will never diverge again onto something else. If they ended up getting onto one of these branches, they were going to start walking the same. It was going to like have them walk and then walk through the same room, but the numbers are different. And then it would walk through the same room, but the numbers are different. And it would walk through the same room, but the numbers are different. And they'd look down and they'd see footprints. They'd be like, hey, let's follow those footprints. And if any of them passed a perception check, they would notice that these footprints are getting like more and more worn as they keep going. And eventually they'd be like, oh, those are our footprints. So there were going to be fewer traps in like the whole grand scheme of things, but you know, still something dangerous down here every so often. Yeah, prove the Collatz conjecture. So I was telling somebody that this is essentially my version of coloring mandalas, is doing, you know, expanding the Collatz prison here. So every time we get to some place where we need to multiply by 3 and add 1, I connect with a blue arrow. And then every time that we went from some number to divide by 2, I went with a red arrow. And just kept going and going and going. but working backwards is kind of hard. So I did figure out that x mod 3 is going to be equivalent to 1, and it's going to branch if x minus 1 over 3 is odd. If x minus 1 over 3 is even, then it will, that number up top will divide by 2 to get to a different number, not do the multiply by 3 and add 1 bit to get to where we are. So essentially I'm reverse engineering this whole thing. And it gets, you know, interestingly difficult as we keep going out. And eventually, again, you can always just multiply by 2 and just keep going forever. But then every time you reach a, what is it? So not 53, but 106, not 35, but 70. This would have been then, right, subtract 1 to get 69, divide by 3, gets us 23. So this would have been a, nope, blue. Here. Get us a 23. Would triple and add 1 to get us 70. So this is the branching of the Collatz conjecture, which is kind of like a family tree, sort of. But basically, like I said, you take any number in the entire, like any real number that you want. Okay, fair enough, mod 6. Yep. Why, thank you. Yeah, this is definitely an NP problem. So basically pick any number you like, start with that number, and then if it's even, divide by 2, and if it's odd, multiply by 3 and add 1. So 883, I should start with something simpler. 83 is odd, so multiply by 3, we get 249, and, nope, sorry, add 1 first. Nope. The hell did I do? Multiply by 3. Oh, right. No. Did I screw this whole thing up? Oh my god. What the hell? Oh, fuck me. Alright. Oh, I'm gonna lose my mind. Okay, cool, cool, cool. 256 minus 1. 255. Divided by 3. Gets us 85, not 83. Oh, shit. Oh, no. Oop, that's not what I want. Oh, screw my life. We'll save that for later. Welp. Psyche. Woo! Absolutely 3 left seconds. 85. hell is gayazo.com? Cool. I just never heard of it before. Right, okay. So, hell, we can even do this one as algebra. As much as you would love that, I'm sure. So, boop. Okay. So anytime you've got compound fractions, so like 3 over 2 plus 8 over 5, all divided by 6 over 5 plus, hell, minus 6/7, because I'm masochistic. So anytime that you've got some sort of compound fractions within fractions, we want to get rid of that as soon as possible. So here, what we can do is we can multiply both the top and the bottom, due to the fact that, again, we have to make sure that this is balanced. So this value needs to stay the same, regardless of whatever. Yeah, I mean, it's probably middle school, but... Alright, so with this, we got to make sure that it's balanced, regardless of how we're doing this. So on the top, we need a 2 and a 5 in order to get rid of the fractions entirely. But these are both prime numbers, so we need to multiply by a 2 and a 5, and then we need to balance it by doing the same on the bottom. Alright, and then on the bottom, we need to multiply by a 5 and a 7. So it's perfectly fine if you want to say, I'm going to multiply by 5 and by 7, and just multiply all 4 of them. That's perfectly fine. You can always do this. But you don't actually need it. So if we want to do this in simplest form, you notice that on the top we have a 2 and a 5. And on the bottom we have a 5 and a 7. The 5 from the top that we used up here, this first one, will also apply to the bottom as well. So we don't actually need this second 5 at all, because right, the 5 from the top is also going to affect the bottom. So to use a simplest form, oh no, do not cross multiply. There are only like 2 situations where you are allowed to use that term. This is not one of them. So we are multiplying across, not cross. Okay, so here we're going to multiply both the top and the bottom by a 2, a 5, and a 7. Or if you want to say, what is this thing? This thing is the least common multiple of the denominators. The 2, the 5, the 5, and the 7. Which is 2 times 5 times 7, which is 70. So if you want to multiply by 70, you can do that. Or you can leave them as individual terms, which I actually prefer. Reason being, you're going to multiply this to all the things. So this is going to be a 3 divided by 2, and the 3 is going to be multiplied by a 2, a 5, and a 7, plus 8 multiplied by a 2, a 5, and a 7 over 5, divided by 6 times a 2, a 5, and a 7, all over 5, minus 6 times a 2, a 5, and a 7, all over 7. And now individually, all these things are going to divide out one of their other numbers. Now it doesn't have to be one number, it could be a lot of different numbers. So one of our divisors, like this one could have been 35, for example. If this was a 35, then it would cross out both the 5 and the 7. not doing that right now. So just, leave that. So here, the 5 here divides out the 5 there. The 5 here divides out the 5 there. And the 7 here divides out the 7 here. So this is going to be equal to what's left? A 3, a 5, and a 7. 3 times 5 times 7. Plus 8 times 2 times 7. All over. 6 times 2 times 7. Minus 6 times 2 times 5. This is going to be 3, 5, and 7 are going to make 35 times 3 is going to be a 105. Plus 8, 2, and 7 is going to be 56 times 2 is 112. Divided by 6 to 7 is 42 times 2 is 84. Minus 6 times 5 is 30 times 2 is 60. So that's going to be a 217 divided by 84 minus 60 is going to be 24. Right, and here we're not divisible by 3. We're not divisible by 2. So that takes care of all the possible factors of 24. We're not going to have any that are both top and bottom. So that's it. So my example up here, yields a value of 217 over 24. I wouldn't. I mean, if it's asking for a mixed number, yes. So yeah, you... Nope. So the one you gave me had an improper fraction, 6/5, and yeah, all the rest were less than or equal to 1. So they were all, proper fractions. So the what to do with your answer after this kind of depends on what the questioner wants. So if you want to know what the mixed number is, you can always do that. In this case, you'd probably want to do long division. Yay! So an 8 would give us 160 times, or plus 32 is going to be a 192. Yeah. So 192, you can go one more. Makes it a 216. Yep. So 9 times 24 is going to be a 216. Subtract that off, you're left with 1. So this would be a 9 remainder 1, or 9 and 1/24. So the name of my game is flexibility. Being able to come up with any answer that anyone could possibly want is really what you want. You're going into whatever branch, the military potentially, that you want to go into, knowing what your immediate sergeant wants, it's going to be helpful. Kind of depends what you're going for. if you mean like... pretty close, but if you're going to say prove the Pythagorean theorem by geometry, then yes, this is rather annoying. I mean, it's supposed to be a square, but that's a little better. It's a right triangle, and these are squares attached to it. So the area of this thing is equal to c squared. The area of this thing is equal to b squared. And the area of this thing is equal to a squared. You can prove the Pythagorean theorem, a squared plus b squared equals c squared, by doing geometry and doing like the whole draw a line going from this point to that point. Come on, come on, really? There we go. To this point. Now take this triangle here and it will be equivalent to this triangle on this side by the side angle side theorem. I hate it when it does that. Aw, that one's not too bad. So there is a Euclidean theorem. Now that I'm saying it, it might not be Euclid. Oops. General sum of angles for polygon. There we go. Sum of all angles in a polygon is equal to the number of sides in that polygon minus 2 multiplied by 180. Who came up with that? Interior angle formula. Who discovered the interior angle formula? Okay, Euclid proved the sum of triangles adding up to 180. Okay, I'm getting like way too distracted by trying to figure out who did it because apparently I like my history. So we'll just erase that for now. So sum of interior angles for a convex n-gon is going to be equal to n minus 2 parentheses times 180 degrees. I don't think I did. So this means that the sum of the interior angles of a trapezoid, which I think is the one you gave us, maybe a kite, what did you give us? No, it's none of the above. It's just a random quadrilateral. But 3 of the angles are equal to each other. They're x. So here you said it's going to be 1, 2, 3, 4. Alright, this is not. There we go. Alright, x degrees, x degrees, x degrees. 45. I mean, there's no explicit formula, so like, it's kind of awkward. Right, so for this, the sum of all angles is going to be 45 plus 3x, which is going to be equal to 360. So we have a quadrilateral, it has 4 sides, we subtract 2, and we end up with 2 times 180 gets you 360. I mean... So 3x is going to be equal to, subtract 45 from both sides. It's going to be 315, which is nicely divisible by 3. So 3 gets you 1, 0, and 15 gets you 5. So if x is 105 degrees, we can get 3 x's and 1 45-degree angle. Just going to then, right, get us that particular thing there. So you get a relationship that exists between the two things. Now, back in Euclid's day, they didn't have algebra. Keep in mind, right, al-Jabr comes from Arabic, or Persian at the time. And essentially means like the recombining, or reordering, or regrouping, or various other things like that. Returning, making whole. And so this was part of a much, much bigger title that I actually can't pronounce. Um, Yep, the compendious book on calculation by completion and balancing. Al-Kitab al-Muqtazar fi Hisab al-Jabr wal-Muqbala. So, again, I can't pronounce it. I don't. Half of those diacritical marks are incorrectly pronounced completely. Written by Muhammad ibn Musa al-Khwarizmi. Var-Muqbala, I believe, is the compendious book part of the title. So, Hisab. I mean, it might not be. I don't know enough Arabic to even remotely come up with this. Anyway. Anyway. So every four-sided shape will always end up having a sum of 360. Every three-sided shape will always have a sum of 180. Again, we can look at that in terms of the number of sides it has here. So number of sides is 3, and it's 3 minus 2 gets us L1, and 1 times 180 gets us all triangles are going to have 180. Right, every new side added is going to add another 180 degrees in total. So we start with n equals 3. That's going to get us, right, n minus 2 gets us 3 minus 2 is 1. And then 1 times 180. And then 4, again, gets us 4 minus 2 is 2. Times 180 is 360. And then every five-sided shape, every pentagon has 5 minus 2 or 3 180s in it. So that's 540, etc. Balancing. That's what it was. So this is also something that you could do, is to say, if you want to look at the sum of the interior angles for any convex n-gon, so n-sided polygon, you could also write this specifically as n and then sum of angles. Right, this is going to have 3, 4, 5, 6, 7, 8. I hit the button on the side of my thing. 7, 8, and then this is going to be again 180, 360, 540, 720, 900, and 1080. What's the question? So, I mean, in theory, maybe. Yeah, I'd have to know what the actual question is because the pieces are separated. Anyway, somebody also asked another question there. Eh. If you could make them work as like U substitution, then it's super easy. But the problem is that you might not be able to. So, really. Okay, so Bertram. Whoa. Oh, gotcha. Proof by strong induction. Interesting. Okay, so we said okay, n greater than or equal to 3. We have f sub n is greater than alpha raised to the n minus 2, where alpha equals 1 plus the square root of 5 all over 2. Or we know that alpha squared is equal to alpha plus 1. Okay. So find p of n, where p is oh, there we go. So basis step said we want, right, f of 3, because again, n must be greater than or equal to 3, is greater than alpha raised to the 3 minus 2. So f sub 3 is greater than alpha to the first. Yeah, I'm just making sure. So we can do as many basis steps as we want to just show that individually we have some numbers that work. 4 is greater than the 4 minus 2, which equals alpha squared, which equals alpha plus 1. So we get 1 plus root 5 all over 2 parentheses squared, which should be the same as 1 plus root 5 over 2 plus 1. So here, this is going to be 1 plus 5 is going to be 6 plus 2 root 5. over 4. Or 3 plus root 5 over 2, which is equal to, over here, right, 2 over 2. So yeah, 3 over 2 plus root 5 over 2. Okay, cool. Yeah, so you can't start with any prior values, because that's just not going to work. But right, it was stated at the beginning that n has to be greater than or equal to 3. So f sub 3 is the first number that we can actually use the formula for. Now, in theory, right, in theory, well, no, okay. If we go back a step to f sub 2, then that's going to be equal to 1, which is going to be equal to alpha raised to the 0 power. So yeah, right, so f sub 2 greater than alpha to the 2 minus 2 is going to be alpha to the 0 is 1, but again, f sub 2, Fibonacci sub 2, is equal to 1, so then that would be equal to that 1. So then this would just not work at all for this formula, because again, we want it to be greater than. So basis step is going to be 1, 1, 1, 2, and then 3 here. All right, so then here, 3 plus root 5 over 2 is 2.618, right, which has a 3 on this side, so it's greater than that, which is true. Right, and this value here, our phi value is 1.618, which again is going to be great. 2 is greater than that. I meant the other way around. Right, 3 is greater than 2.618. 1.618 is what we got here. Okay, so we assume that this is true for some n. So that f sub n is actually greater than alpha to the n minus 2. Now we need to show that this works for f sub n plus 1 being greater than alpha to the n minus 1. Okay. So with it being greater than, that's kind of tricky. Right, so we have to get from here to there. So without me peeking, right? To get from here to the next step, we can multiply both sides by another alpha. Right, this would just be alpha to the n minus 1 less than this thing. Can we show that this is now going to be less than want that this is going to be less than f sub n plus f sub n minus 1, or this is going to be less than f sub n plus 1 eventually. Alright, give me... yeah, because the n minus 1 is going to be n minus 2, but then you plug in n plus 1 for n. So that's kind of where we're going with it. So I'll be back in 1 minute. Give me... give or take. Alright, be right back. Alright. And boop. Alright, so that's weird. It's really amusing. I just popped up in my own chat as a subscriber. I'm not even talking about my Obi-Wan Pez account. I'm talking about my N-Simplex Pachinko account. Yeah, no. That's not how that works. But apparently I have subscriber rights or something. I don't even know how that works. Did it actually go to an ad? It must not have, because I still have here that pre-roll is currently on. Alright, whatever. I guess new people are going to have to suffer through pre-roll ads, so... oh well. Right. Switch back. Okay. So we want this thing that either we're going to add something to the other side, which again is not quite going to work. Or let's see, what else do we have here? Okay, Okay, so alpha could be equal to alpha squared minus 1. I don't know if that's going to help any. Oh, actually, yeah, this. So instead of multiplying, I don't know, maybe it'll work. Instead of multiplying, we could try adding, in which case we get f sub n is greater than alpha to the n minus 2. Then we add f sub n minus 1 to both sides. Right. Over here, f sub n plus f sub n minus 1 is going to be f sub n plus 1, which is greater than alpha to the n minus 2 plus this, maybe not. Ooh, that might have done it. Yeah, no. So I'm trying to add the previous number to create f sub n plus 1. So remember that f sub n plus 1 is going to be equal to f sub n plus f sub n minus 1. Right. So we're trying to create f sub n plus 1 from the previous terms, which then means that this is going to be greater than alpha sub n minus 2 plus f sub n minus 1 is going to be greater than alpha sub n minus 3. So if you're not sure where these numbers are coming from, right, we did n gets us, f sub n gets us alpha to the n minus 2, and then here this is f sub n minus 1, this is n minus 1 minus 2. Okay, so then here is still going to get us f sub n minus 1, which is greater than. Now here we could something with n minus 1. Alpha sub, or raised to the n minus 1 multiplied by, I don't know if this is going to work, but just try something. Alpha to the negative first, alpha to the negative second. I don't like it. Wait. Take out n minus 2. We'll be left with 1 plus alpha to the negative 1. I don't think that's going to help. Right, or n minus 1 times alpha to the negative 1 plus alpha to the negative 2. I don't think that's going to help either. Oh, maybe. Processing. Processing. Yes. Okay. Okay, okay. I got it. I think. If we do n minus... What the hell? Let's just do n minus 3 for right this second. And I think this is gonna... Yeah, this will work. Alright, so alpha to the n minus 3. Okay, it may not work, but it'll look good. If we're taking this out, then this leaves this with a 1 extra alpha. And then this just leaves a plus 1. Alpha plus 1 is equal to alpha squared from up here. Yep, that's it. So this is alpha to the n minus 3. This is alpha squared. This is going to be alpha to the n minus 3 plus 2, which is going to be alpha to the n minus... Hang on. I want this to be explicitly in the other form. So this is going to be like minus 1, or this is x plus 1, n plus 1, parentheses, minus 2. That's what we want. There we go. See, it's just poking the bear enough times that it doesn't bite you, but still. Do not poke bears. Disclaimer. Alright, how are we all doing? Mine is a little more rigorous, but you know. Because I added literally the same thing to both sides, but I just went one further and said we have this intermediate stuff that we're never actually going to use. I mean, that's nothing. You ought to see the right, the expression for the sums of squares. No, wait, hang on. N. So for n equals 1, we've got 1, 2, 3 over 6 is equal to 1. Oh yeah, I saw that too. Uh-huh. Yep, that was Bertrand Russell. Not Bertram 404. Yeah, did you see Jade's video? So they wanted to like guarantee that anybody reading this would be able to understand it and would actually be able to say, yes, actually 1 plus 1 equals 2. You know, the concept of 1 by itself is like a thing. This one is going to get us k going from 1 to n plus 1 of k squared is then equal to here. This is going to expand out. We're going to get 2n cubed plus yeah, 2n cubed plus 2n 3n squared plus 1n is going to be just 1 plus 1, so n, plus this thing, n squared plus 2n plus 1. Oh, shoot, messed up. Because that isn't just added onto this fraction willy-nilly. This is going to be multiplied by 6 over 6. So this is going to be a 6n squared plus 6 and 12n plus 6. All divided by 6. So then that's going to be equal to 2n cubed plus 9n squared plus 13n plus 6 all over 6. Yeah, so I watched Jade. What's her handle? Yeah. No. There we go. Up and at 'em. Yep. Why it took 379 pages to prove that 1 plus 1 equals 2. Uploaded 5 days ago. I mean... Alright. Interesting. Anyway. Yep, see you, Bertram. Off to prove this last little bit here, and then we'll possibly raid over to somebody else. Unless anybody else has any questions, feel free to drop them in the chat, as always. Alright, so with this thing, we want to factor out n plus 1. That's our goal. So here, if we can factor out n plus 1, we can divide using synthetic division by this -1 factor, which is the 0 of this particular thing. Yeah, definitely. All right, so 2, 9, 13, and 6 are the coefficients. And here we get a 0, bring up a 0. This adds to become a 2, multiply -2, add 7. Multiply becomes -7, add becomes 6, multiply becomes -6, and add becomes 0. Oh, good. It worked. So this says that we're going to end up with n plus 1 times 2n squared plus 7n plus 6 all over 6. Okay, which is equal to then n plus 1 multiplied by, and we can factor, you know, again, this should be a -2 factor that we're taking out. So then this should be 2, -4, 3, -6, and 0. So this factors out n plus 2 as well. And then we're left with a 2n plus 3 multiplied by 6. This is not exactly the same as what we have up top, but that's okay. So this is going to be an n plus 1, a parentheses n plus 1 plus 1, and a 2 parentheses n plus 1 plus 1 all over 6 is equal to sum as k goes from 1 to n plus 1 of k squared. Alright, so now from the original equation, from the original formula, all of our n's have been replaced with n plus 1s. So they're in the appropriate locations, and then we have this. All right, how we doing? And as always, if I missed anything, please let me know. All right. I think that's going to be it for the night then, if nobody else has anything. And let's go raid over to... Who do we got? Who do we have tonight? Alex Ward, always fun. Michelle Boyd, been on for a couple hours at least. She's fun too. H-Ray is cooking tonight. Selena's doing her usual Castlevania. Aaron Stevie's doing Final Fantasy VI. I know a lot of people really like that one. Okay, let's go over to Boss Lady because tonight she is doing a crazy on foot thing for Elite Dangerous. There is a planet called Mitterrand's Hollow, which orbits its, which is a moon, which orbits its main planet once every 90 seconds, I think. You cannot catch the moon. You have to wait until the moon catches up with you in order to land on it. So this is an absolutely insane feature of the game. So, have a good night, everybody. Hope you had some fun tonight, and let me know if you have any more math questions. My channel name at gmail.com is easiest way to get some sort of question to me, and I check it, you know, occasionally. All right, have a good night, everybody. This is Obi-Wan Pez for Ensimplex Pachinko. I will see you next Tuesday for math stuff, or this Friday for more Soma. We're going to try to finish up the spooky games. Alright, see y'all later.